Welcome to lecture number 29 for ECE 341 Random Processes chi-squared test. Now, the previous lectures we looked at a t-test. A t-test is a test of a mean, such as what is my reaction time, what is the average per die roll. A chi-squared test is a test of a distribution. It is used to test whether a die is fair, such as that has a uniform distribution, test whether distribution is normal versus Poisson or geometric. And the chi-square test is a type of a gamma distribution. What you're doing is I have the actual observed frequency of events, what they should be, take the difference and square it, add them all up. So the answer is always positive. That makes it a gamma distribution. And what the gamma distribution looks like, chi-squared looks like, is depends upon how many bins you have. What I do is I take the data and split it up into bins and count how many times the data winds up in each bin versus how many times it should wind up in those bins. The degrees of freedom is number of bins minus 1. You need at least 2 bins. If I have 1 bin and say I rolled the dice 50 times, I got 50 results, what's that tell you? Absolutely nothing. Got to have at least 2 bins so I can say even versus odd, the number 1 versus other numbers, something like that. If I have 2 bins, meaning 1 degree of freedom, there's what the chi-squared distribution looks like. 2 degrees of freedom, 3, 4, 5, 6. That's a type of gamma distribution. To explain a chi-square distribution, it's probably easiest to give examples. So let's start with a die. Suppose I have a 6-sided die and I roll it. If this is a fair 6-sided die, I should have each number come up 1/6 of the time. So the procedure to conduct a chi-square test is I first define how many bins I have. If I have a 6-sided die, I could take 6 bins, 1 for each number. I could have 2 bins, even versus odd, 1 versus the numbers 2 through 5. Many different ways of doing it. However I do it, define m bins. Next step is I collect data. I roll the dice a bunch of times and count how many times the data roll winds up in each bin. I then compute the chi-squared score. That's the expected frequency. That's the number of rolls times the probability of each bin, in this case 1 in 6, minus the observed frequency, how many times they got a 1, how many times they got a 2, take the difference and square it, divided by the expected frequency, n times p, add them all up, that's your chi-squared score. I'll then use a chi-squared table to convert that chi-squared score into a probability. So let's start out with a fair die. So here's a MATLAB program that will roll a fair-sided die, fair 6-sided die, 120 times. And what that looks like is this. So I clear my screen. I run the program one time. Here's a fair die. If I run it, here's how many 1s, 2s, 3s, 4s, 5s, and 6s I got. And every time I run it, I'm going to get a different answer. It's a random process. Suppose I roll the dice 120 times, and here's what I get. 18 1s, 27 2s, 25 3s, and so on. Once I get those results, I calculate the chi-squared score. The expected frequency is, if this is a fair die, the probability of each number is 1 in 6. I roll the dice 120 times, so n times p, n is 120, there's p, n times p is 20. Take the difference squared divided by np. So this is 2 squared divided by 20, 7 squared divided by 20, 5 squared divided by 20, and so on. That's the chi-squared score. Add them all up, I get a number. There's your chi-squared value. Now use the chi-squared table to convert that to a probability. And this is what a chi-squared table looks like. I've got the degrees of freedom. That's the number of bins minus 1. And you need at least 2 bins. A single bin is meaningless, so that kind of tells you that. A single bin means no degrees of freedom. That's nonsense. I have to have at least 2 bins. In this case, I have 6 bins, meaning 5 degrees of freedom. That's the left side. The top is the area, the probability of rejecting the null hypothesis. If the data is very, very different, I get a high chi-squared score. If the data matches up really, really well, I get a low score. I take the number that I get and go through the table and see what the probability is. And what these numbers mean, if it's a really high probability, that means reject the null hypothesis. In this case, kind of lousy spelling. Okay, reject the null hypothesis. This is not a fair die. That's if the number is really high. Over here, this actually kind of tells you that maybe I fudged the data. The data is too good. I cheated. In the middle is where you typically get the answer. That's no conclusion. That means I don't have a loaded die. I didn't fudge the data. That's typically what you get. So I can use the chi-squared table, or I can use StatTrack. If you go to StatTrack, there's a chi-squared table. You input the degrees of freedom, the chi-squared critical value, hit calculate, and it gives the probability of rejecting the null hypothesis. Now, personally, I would use StatTrack. Plugging those in, I had a chi-squared value of 6.2, 5 degrees of freedom, meaning 71% chance of rejecting the null hypothesis, 71% chance this is a loaded die. That's kind of no conclusion. This actually is a fair die. MATLAB is pretty well debugged code. The RAND function is pretty good. But just with random data, I can get numbers like this. So typically say if it's higher than 90%, I think it's a loaded die. I didn't get that. I didn't get 1%. It's not fudged data, it's real data. Basically no conclusion. That's typically what you get with the chi-squared test. Now that's with 120 rolls. If I roll the dice 1,000,000 times, you can kind of see the answers here. This is where MATLAB scripts are kind of nice. This is 120 rolls. Make that 1,000,000 rolls. And here's my answer. Take one of those, calculate the chi-squared score. That'd be the difference between the actual results and the expected results. Here, n is 1,000,000, p is 1/6. Take the difference squared, add them all up, divide by the expected frequency, and I got a chi-squared score of 3.4, and that gives me 37% chance. And every time you run this, I'm going to get different answers. So for example, if I run it, I got a chi-squared score of 8, 14, 4, 4, 11, 4, 3, 1. Now occasionally, looks like it's not a fair die. It's a random process. But typically, you'll get a chi-squared value that means, let's go back over here. Typically, I'll get numbers between, say, 1.6 and 9. So it's not really good data. It's not really bad data. It's just random data. And that's what I'm getting in MATLAB. Eight, usually between 1.6 and 9. Normally what I get. Second case, suppose it's not a fair die. Suppose it's a loaded die. Can I detect that with a chi-squared test? And what a loaded die looks like, there's actually kind of a interesting book I read back in the 70s on cheating and craps. Haven't found that book since, but really fascinating book. Talks about craps, dice games. They've been around since the Roman Empire. Many ways to cheat. One way to do that is if you have dice like this, I put a lead weight on one side of the die, so when I roll it, that lead weight tends to wind up on the bottom. That affects the odds. If you're playing a game like craps, in craps, the way you play the game. So for example, this is how you play the game of craps. I have a set of dice. They're tossed to a person. People place their bets. You toss the dice, and the numbers come up. If on the first roll, you get a 7 or 11, you win. On a 2, 3, or 12, you lose. On the other numbers, it comes up with a point. So suppose it was a 6 came up as the point. I then keep on tossing the dice. If I get a 6, I win. If I get a 7, I lose. On the other numbers, if those come up, then you get payoff. So if you can affect the numbers that wind up on the roll of the die, that affects the odds, and you can start winning. That is cheating at craps. So this is one of the earlier ways of cheating at craps. You would load the dice. Well, to avoid that, what casinos did is they now take the dice and make them have nice square corners. If you have a sphere, then the heavy side always winds up at the bottom. The less sphere-like the die is, the less impact that loading has on it. So they'll make this a nice square die, and they'll also make a clear die, kind of like this. With clear dice, you can see through them and see the loading. So you can't really load the dice that way. But not to be thwarted, what you can still do with dice is if you have a clear die, you can drill out the 6s and fill them with titanium or tungsten, something really heavy. Cover them up, paint it, look like a normal die. So now the 6s wind up on the bottom more often than not. To avoid that, again, what they do in craps is they kind of watch you see what you're doing. The operator watches the dice very carefully. You are not allowed to cup the dice in your hand. If you do that, they lose sight of the dice. You might be switching them out. So they get very upset. You got to see the dice at all times. If the die wind up on the floor, they retire the dice and bring in a new set of dice. And even then, dice get swapped out on the dealers. There's other ways to cheat as well. One person came up with a strategy. You can take one of the dies, put a 6 on it, put the other die on top, cup it in your hands, and then roll it. Give a lot of spin, so the dice would just slide on the table. If they just slide, they don't roll, and you have one die coming up. Well, to avoid that, they changed the rules of craps. So now if you watch them, they then changed the rules that when you toss the dice, it's got to hit the back wall. Notice when he tosses the die, it hits the back wall and bounces off. Well, someone else came along and came up with a strategy. They got really good at tossing the dice, so they would hit the back wall right on the corner and stick. The bottom die wouldn't roll, top one rolls off. If you do that, you can set the number on the bottom die. Well, to avoid that, they then changed the rules that when you hit the back wall, you have to hit the back wall 2 inches above the base, then bounce off. Plus, they make the dice square with nice sharp corners, so it rolls. See that rolling? Makes it harder for a certain number to come up. That's what the casino wants. They want it to be random. But again, to thwart that, you wind up with loaded dice, where you drill out the 6s, fill them with titanium. So to combat that, what the dealers do is they will eventually retire the dice, say after every 30 minutes, put them in a bin, bring out a new set of dice. So even if a loaded set of dice winds up on the table, they eventually get retired. One of the strategies with loading dice is you have to have a die that's not really obvious that it's loaded, so the dealer doesn't notice it. But you can tell when the die is in play. And what they do, if you look at the numbers, like the 3. The 3 goes between the 2 and the 6, not the 1 and the 2. If you rotate the 3, that's a non-standard die. You can detect that's a loaded die, not one of the pair dice. So when that die is in play, you know to start betting. It's got to be subtle enough the dealer doesn't pick up on it, but other people do. That was a book that's on the history of cheating and dice. Kind of an interesting book that I read back in junior high. Just strategies, problems I ran into in Vegas. On MATLAB, I can do the same thing. For example, if I have something like this, 10% of the time, I'm always going to roll a 6. Otherwise, it's a fair die. Can I detect 10% loading? Well, in MATLAB, here's kind of what that looks like. You can change the loading with this number right here. So if I have 10% loading, here's the numbers I'm getting. I'm getting a few too many 6s, but it's not really obvious. If I make it really obvious, like 90% loading, let's do this. Clear the screen. So there I have way too many 6s. That's pretty obvious that this is a loaded die. Suppose instead of 90% loading, I do 50% loading. Half the time it's a 6, half the time not. That's still pretty obvious. Let's make it 10% loading. And I'm getting too many 6s, but not really obvious. Can I detect that there's too many 6s with a chi-squared test? Well, what I do is I kind of do what I did before in the program. I roll the dice, in this case roll it 120 times, and observe how many times you got a 1, 2, 3, 4, 5, and 6. Compared to the expected frequency, take the difference squared, 4 squared divided by 20, 2 squared divided by 20, 10 squared divided by 20, add them all up. You get a chi-squared score, 11.5. To convert that to a probability, I use a chi-squared table. I've got 6 spins, meaning 5 degrees of freedom. I've got the number 11.5. That's right around here. It's about 95% chance this is a loaded die. If I repeat with 1,200 rolls, the chi-squared score is now 68. That makes it really obvious this is a loaded die. So with enough rolls, I can tell that the die is loaded. Of course, if this is a casino and I'm betting on it, after 1,200 rolls, I'm probably broke. At least I know why I'm broke. And it doesn't just apply to craps. Here's another game in Vegas called roulette. What they do in roulette is they have a wheel that they spin, toss a marble around, you see the marble spinning. People are betting on different numbers. When the marble stops, that's the winning number. If you bet on the winning number, you win. And there's other ways to bet too. You can get black versus red, even versus odd, stuff like that. When the marble stops, waiting, waiting, waiting. There it is. There's the winning number. Can't see what that is. Well, whatever that number is. That number won. Everybody else loses. Well, kind of another cheating in Vegas. Somebody, years back in the 70s, had the hypothesis that do all numbers come up equally? Is this a uniform distribution? Well, the roulette wheels are built by people. People are fallible, so maybe some roulette wheels, some numbers come up too often. So what he did is went to Vegas and observed the roulette wheels, what numbers were coming up, and found that sure enough, some numbers were coming up more often than they should. Started betting on that and made money. Well, when you start making money in Vegas, they kind of pay attention to what you're doing, try to find out why you're winning, and kind of found out the strategy that, yep, if you have enough data, you can see that some numbers are coming up too often. So what they do now is when they spin the wheel, I want to have the wheel coming up as often as I can because I'm wasting money or time and money right now. They want the wheel to go kind of slow. If it goes too fast, it takes too long for the numbers to come up. But if it's too slow, you kind of know which number is going to come up as the conditional probability. Here it went around. You see there's looks like probably 20, 30 rotations of the wheel as it goes around. Really hard to predict what number is going to come up based upon where you release the marble. But again, the roulette wheel may not be perfect. Some numbers might come up too often. Well, what they do now is at the end of the day, they take the roulette wheels, put them in a back room, shuffle them, bring them out the next day so you don't know which wheel is on which table. They make all wheels identical, or as close to identical as they can. If you touch the wheel, they get really upset. They think that you're trying to mark the wheel so you know which one it is the next day. They get very upset if you touch the wheel. Do not do that. If there's a mark on it in any way whatsoever, they will retire the wheel, bring out a new one. If you sit there and start taking notes as which numbers are coming up, they'll ask you, please stop doing that, please leave. You're not supposed to take notes. You're just supposed to gamble and lose. That's part of the game. That's again a chi-square test. Do some numbers come up more often than they should? Here's a question for you. This is also chi-square test. How loaded is too loaded? Okay, we kind of looked at that before, back in MATLAB. If I get greedy and say I'm going to load the dice with 99% loading, here's what I get. It's pretty obvious I'm getting too many sixes, so 99% loading is way, way, way too much. If I make it 1% loading, it's really hard to tell I'm getting too many sixes. How about 10% loading? Again, that's kind of hard to tell. How loaded is too loaded? How loaded can I make the dice and get away with it? That's a chi-square test. So to figure out how loaded I can make the dice, I have to define some terms, such as when I say detected, what do I mean by detect? I'm going to assume that I'm going to have a 5% chance of being caught, where the chi-square score is 95%. I have to assume after how many rolls? 1 roll, 2 rolls, 10 rolls, 100 rolls. Let's assume 120 rolls. So if I have 6 spins, a 95% chance of getting caught, I need a chi-square score of 11.1. That's from the chi-squared table. Again, going back to the chi-squared table, I've got this number right here, 11.07, 95% chance that the die is loaded, 5% chance, well, 95% chance of getting caught. Or that from the results I can tell that the die is loaded with a probability of 0.95. Let's assume I have 6 spins, I have x too many sixes, and the x's are distributed among the other 5 numbers equally. So if I do that, I'm going to roll the dice 120 times. I should get 21s, 22s, 23s, and so on. I'm getting x, too many sixes. Those x's are taken away from the other numbers equally. I can have form the chi-squared score. Take the difference squared, divide by 20, difference squared, divide by 20, difference squared, divide by 20. Add them all up. I get 1.2x squared over 20 is 11.5. Solve for x, I get 13.84. So that means you can have an extra 13.84 sixes, or 11% loading, and get away with it. So back here in MATLAB, if I made it 11.8% loading, I can get away with that 95% of the time. Just can't get too greedy. Can't make it like 20%. That's one way to calculate it. Another way to calculate it, suppose I just have 2 bins. I have too many sixes. Those x's are spread out among the other numbers. I don't really care how. The probability of getting a 6 is 1 in 6. The other numbers are 5 and 6. I have x too many sixes. I take those x's away from the other numbers. Add them all up. Take the difference squared, divide by 100. Difference squared, divide by 20. Add them all up. Now, since I have 2 bins, meaning 1 degree of freedom, the chi-square score I'm looking for is right here, 3.84. If this sum is 3.84, x is too large. Solve for x, I get x is 8. So I can get 8 too many sixes, or 6.7% loading, and get away with it 95% of the time. With a chi-square test, I can determine how greedy I can get, how much I can cheat and get away with it. Well, there's an application for that. Ever watched the movie, The Imitation Game? This is about Alan Turing breaking the German Enigma code. The Enigma machine was the way the Germans were sending encoded messages to their subs, and it was hard to break. It was a pseudo-random sequence. You have to know the settings on the machine to break the code. Once they broke the code, they had a problem. If they respond to every German message, the Germans will quickly realize that we cracked their code and change the code, in which case you're back where you started. On the other hand, if you never respond, then there's no point in cracking the code. How many times can I respond to the German messages without the Germans realizing that we know what they're saying? That's a chi-squared problem. Same as we just did with the six-sided die. How loaded can I make it without the person realizing that the die is loaded? How many times can I respond to the Germans without the Germans realizing that we know what they're saying? So if you ever watch the imitation game, that's what they're talking about. That's a chi-squared test. Another thing you can do with a chi-squared test, you can spot when people fudge the data. If the data is too good, that shows up on a chi-squared table. For example, if I have a chi-squared score that's really large, that means the die is loaded. If the number is really, really small, that means that data could happen, but it's really unlikely you'll ever see data that good. If you're consistently getting data that's too good, that's kind of proof that you're fudging the data. For example, suppose I'm paid to roll the dice 1,000 times, but I'm kind of lazy. I don't want to do that. I'm only going to roll the dice 150 times, then add, or 100 times, then add 150 to the total. So I'm going to start out with the number 150, roll the dice 100 times, and report. These are the die rolls. I rolled the dice 1,000 times, that's what I got. Can I tell that I fudged the data using a chi-squared test? Well, to do that, let's calculate the chi-squared score. Here's how many times I should get each number with 1,000 rolls. Here's how many times I actually got it. Take the difference squared divided by 166, difference squared divided by 166, add them all up, I get 0.44. From StatTrak, convert that to a probability. I've got 6 spins, meaning 5 degrees of freedom. Probability of that is 0.5%. The odds are 200 to 1 against ever getting data that good. At data that good, you'll get kind of suspicious that I fudged the data. If I'm consistently getting data that good, you know that I'm cheating. I'm not rolling the dice. I'm just putting down numbers, rolling the dice 100 times, adding 150 to the results, calling that good. That shows up on a chi-squared test. Suppose instead of generating random numbers, I just go through a random sequence. And here I'm just going to go through the sequence 526, 341, then it repeats 526, 341. In practice, I'd actually make the sequence longer, so it's harder to detect, but same idea. Let's just assume I have the same sequence right here. Well, when I come up with that sequence, I'm going to have each number appear the same number of times, because otherwise I'll have too many 5s or too many 1s. People will notice that. Have each number appear 1/6 of the time. When I go through the sequence, I'm going to have exactly 21s, 22s, 23s, 4s, 5s, and 6s. Find the chi-squared score. Chi-squared score is 0. Probability of that is basically 0. I'm never going to get data that good. You can kind of see that in MATLAB. When I have a fair die, let's go back to the fair die, I should get 21s, 22s, 23s. I didn't. You're never getting, well, almost never getting exactly 20, 20, 20, 20. That's just too good. That shows up on a chi-square test. Probability of that happening is actually really unlikely. Get data that's that good, I can tell you fudged the data. You didn't actually roll the dice. With the chi-square test, I pick up that this is not a random number. This is actually a deterministic sequence, and it shows up in the chi-square test. You can actually look at history and see that some very famous scientists fudged their data. Mendel, for example, you can show that Mendel fudged the data. Mendel came up with the idea of a dominant gene and recessive gene. What that says is if I have a dominant gene and a recessive gene, if I have 2 cases of the dominant gene, I get the dominant characteristic, round, yellow, purple, stuff like that. If I have 2 instances of a recessive gene, I get things like wrinkled, green, white, constricted. If I have a dominant and a recessive, then the dominant gene shows up. That's the reason for the word dominant. What Mendel's experiment did is he came up with a purebred dominant gene, purebred recessive gene, cross them, and what you get are hybrids. What hybrids do is it always has the dominant gene, So in the first generation, or second generation, I get the dominant gene being expressed. In this case, if dominant is green, I get all green. If I cross a hybrid and a hybrid, what I get is something like this. The chance, I'm going to pick one gene at random from one of them, one gene at random from the second one. There's a 1 in 4 chance I'll have 2 recessive genes, a 3 in 4 chance that I'll have a dominant gene in one of these two. What Mendel showed is that if I cross the second generation, the third generation is 75% dominant gene, 25% recessive gene. Now we know that Mendel fudged the data because you're not going to get exactly 75%, 25%. You can see that in MATLAB. So here I'm going to flip a coin, heads or tails, two-sided die basically. 1 or a 0 would mean recessive gene, 1 is dominant gene. If I have, well, do that, I'm going to have 2 recessive genes, 1 recessive gene, 2 dominant genes. So it should be 25%, 50%, 25%. This number right here is what I'm looking at. I'm not going to get 25% recessive genes. On average, I should, but this is a random process. Occasionally 25%, like here's one, but that doesn't happen very often. If you're truly running the experiment, you should get, on average, 25%, but each run is going to be different. Well, Mendel always got 25% recessive gene on the third generation, showing that his theory is correct. That's not going to happen. Or at least it's very unlikely that that happens. And that happened with Mendel over and over again. Plus, there are other problems with this experiment, like the first generation wasn't always purebred. But either way, you can kind of show that Mendel fudged the data. Mendel's argument was that if it wasn't exactly 3 to 1, people wouldn't believe him, and he was right. So he fudged the data so people would believe that he was right. Well, fudging the data to fit your theory isn't how you're supposed to do research. That shows up with a chi-square test. The data was just too good for Mendel. You're not going to get that kind of result. Chi-squared doesn't just apply to discrete distributions like dice and genes. It applies to continuous distributions. So to use a chi-square test with a continuous distribution, the procedure is as follows. First, you split up the data into m regions. For example, if I have a normal distribution, I can split it up into 8 regions, 1 for each standard deviation. Once I split up the regions, I know the probability of each region. Here's the first region, probability of the second region, third region, and so on. Once I know the probabilities, I can find the expected frequency, n times p, then run an experiment. Count how many times the data winds up in each bin, and then do a chi-square test. So for example, suppose I take this. This is something we looked at before. If I add 12 uniform distributions and subtract 6, that looks like a normal distribution. That's the central limit theorem. Can I tell whether that is or isn't a normal distribution using a chi-square test? Well, to do that, what I do is I split up the region into m regions. Let's use 8 regions, 1 for each standard deviation. I'll then generate n random numbers and count how many times it winds up in each region. That's capital N. I can use a StatTrack or a MATLAB or a normal distribution, calculate the probability that the data winds up between 0 and -1 standard deviation, between -1 and -2, -2, -3, and so on. That's p. N times p is p times 100. That's the expected frequency. Now calculate the chi-square score. What's the difference squared divided by np, difference squared divided by np, difference squared divided by np. That sets up your table. So here's the probability of each region, n times p, n, difference squared divided by np, difference squared divided by np, add them all up, get my chi-squared value. Once I have the chi-squared value, convert that to a probability using StatTrack or a chi-square table. Here I've got 8 bins, meaning 7 degrees freedom. P is 31%. What that tells me is I've got no reason to expect that this is not a normal distribution. I've got no reason to think that I fudged the data. It's not too small, not too big. No conclusion. That's typically what you get. So with 100 data points, it's really hard to tell that adding 12 uniform distributions, subtracting 6, is not a normal distribution. Let's repeat with 100,000 numbers. With 100,000 numbers, I now have a chi-squared score of 36. Probability is 0.9995. So with enough numbers, I can actually tell that this is not a normal distribution. It takes a lot of data to tell that, though. And where the data shows up, it shows up in the tails. It's really unlikely I'm more than 3 or 4 standard deviations out. But it is possible. Where it really shows up is at 6 standard deviations out, I will never get a number more than -6 or less than -6, more than +6. Versus a normal distribution, it can happen. Not often, but it can. So the tails are where you can see the difference in the two distributions, but it takes a lot of data to see that. So this actually is not a normal distribution. For all intents and purposes, though, it's pretty darn close. So that's a chi-square test. A chi-square test is a test of a distribution. The procedure is to split the data into n bins, or m bins, and calculate the expected frequency compared to the observed frequency. Take the difference squared, divide by expected frequency, that's the chi-squared score. Then convert the chi-squared score to a probability using a chi-squared table. With a chi-squared test, I can do things like detect whether die is loaded, detect whether data is fudged, or see if the data is consistent with an assumed distribution. That's a chi-squared test. And that's lecture number 29 for ECE 341. The next lecture, we'll go through a bunch of examples of a chi-square test.